Okay. Good afternoon. Okay, today we'll try to finish time-dependent perturbation theory. Let me summarize what we did last time. So we decided to consider the following problem. H0 plus lambda v, lambda for the usual purpose. Okay, so a time-dependent problem where there is some perturbation that depends on t. And we decide to write an equivalent equation for the expansion of psi of t, which we said can always be made in terms of the unperturbed states of H0, the ones that we previously called phi n0, all right? But we omit the phi n0 because there is nothing else than them, okay? And we'll have, in general, such an expansion, but in order to simplify a little bit the writing, we have included phase factor where these are the unperturbed energies of H0. So again, previously we were calling them En0, but now, since there is nothing else but them, I omit entirely the 0. All right? Okay. Then we show that an entirely equivalent equation for the Cn can be obtained. Okay? So it's entirely equivalent to just the Schrödinger equation upstairs, and it gives I h bar, the derivative with respect to time of Cn of t, equal to a sum over m. Let me copy with the notation of last time. Then I have e to the I omega n m t. Then I have lambda v. No, the lambda we can throw away because well, let's still use it. Okay, lambda v n m of t times c m of t. Okay, so this becomes a first order problem for the infinite set of functions Cn of t. These are functions just of time. And you see that it looks like a big matrix multiplying the vector, but the matrix contains the matrix element of the perturbation. Okay? So these objects are phi n v of t phi m. And similarly, these excitation frequencies are just En minus Em divided by h bar. Okay? So in this way, this is totally equivalent to the Schrödinger equation. Then we decide to set up a perturbative scheme in which we identify a zero-order term plus a first-order correction plus a second-order correction and so forth. And we notice that due to the fact that there is one more lambda on the right than on the left, the recursive equation is very, very simple. In fact, I could, in principle, just copy the previous one. So this one, to order, say, p, depends, you can eliminate the lambda, depends on the previous order correction on the right. Okay? So it's totally recursive. I can write that for the zero order, I have equal to 0 because there is nothing else before, and therefore these quantities are time independent. Then you can put the zero order terms here and obtain the first order. You put the first order there, you obtain the second order, so on and so forth. Obviously, this, once you substitute some given functions on the right, this is no longer a differential equation. I mean, it's a very simple equation in some sense. You can integrate it directly both sides, and by successive integrations, okay, you obtain all the corrections, okay? A particularly useful case we discussed last time is when as a function of time, the perturbation is turned on at a certain time t0. So before t0, the system is unperturbed. The system is governed by this, and perhaps is in a single given eigenstate, say phi I. Okay, the initial eigenstate of the system is a given single state. Okay. Now this t0 sometimes is 0, sometimes is minus infinity. It doesn't matter. It's just a fixed reference time before which you essentially know the state of the system to be just, for instance, a single eigenstate of the Hamiltonian. This immediately fixes for you, due to the fact that the Cn 0 order are just constant. This means that for all times, once you have fixed here the Cn 0, you have the remaining thing. So, for instance, this object would tell that the Cn would be delta Ni, the initial selected state, times nothing, just 1, okay, for all times. Now, once you have this, you can, for instance, put it in here and obtain the first order correction, and indeed then by integrating we got the following formula, okay, which is the one I would start again from. So the formula I get is the following: Cn first order corrected as a function of time is simply the integral from t0 to t in the t prime. You have I and h bar here in the denominator, and then you have to integrate e to the I omega n I. Sorry for the notation is perhaps not the most lucky one. I'm calling I the initial state to remind initial, but I is sometimes also the imaginary object, so please not be confused by this, okay? So in any case, this is the oscillatory factor that always appears, and then there is a matrix element that is Vni of t prime. Okay? So this simple integral provides for us the correction to first order to the coefficients that appear in the state. Okay? Good. At this point, I can ask myself what is the probability, for instance, of having excited the system into a certain eigenstate, whatever I want, n, for instance. The probability is simply the modulo square of this object. By the way, you always ask what is the probability of having excited into some different state, because, I mean, the initial one is what is populated by 1. So for the initial one, you will have 1 minus something else, some small thing that starts decaying. For the remaining one, you start from 0, and you start building amplitude, okay? So is this clear? I mean, the initial coefficient, so for n equal to I, you start from 1, and evidently, after t0, this thing will have to decrease. On the contrary, all the others, like the n different from I, they are 0 at the level of C0, and then they grow because of this first order and second order and so forth. Okay? So you usually ask what is the probability of having a certain state n. Obviously, the total normalization of the state is conserved. So if you sum the square of all Cn, okay, modulo square at all n, this will be always 1. Okay? So you know immediately that the sum of all probability of exciting the system okay, the sum for all n different from the initial one should be equal to 1 minus the probability of finding the system in the initial state I. Is this clear? Okay, so whatever is missing from here will be acquired by all other components. Okay, so this is, okay, so the other components are just obtained by, to first order, by the square modulus of this object. We did a few exercises, okay, so just turning on adiabatically perturbation, turning some electric field with a Gaussian and switching it off, and so on and so forth. We recovered, in particular, the first order result for time-independent perturbation theory with this adiabatic switching. Now, I want to do a very important case, which is when this object here depends on time in a periodic fashion, okay? So I will do the following particular case, where this coefficient here are given by v and I, some fixed coefficient, times cosine of omega t. Well, omega t prime, because I have called t prime the integration variable. Okay? Is this clear to everybody? So the v, the potential you put, oscillates in time with a pure cosine. Obviously, this is not the most general choice, but yeah. This is the next case I want to treat. It's particularly useful because with very good approximations, if you send an almost monochromatic electromagnetic field, okay, on an atom, the electric field, the vector potential, everything oscillates with a single frequency. And therefore, essentially, you will have cosine omega t or sine omega t impinging on your system. Okay? So this is a particularly useful for many spectroscopic experiments. Okay? All right. So how do you do this calculation? Well, it's indeed very simple, because after all, the cosine is nothing but e to the I minus I omega t prime plus e to the I omega t prime divided by 2. So you see that in the end, you only have to integrate exponentials, okay? Oscillating exponential, which you know how to do, okay? So this is a very simple exercise. Let's continue the thing. So this integral is 1 over I h bar. The integral, okay, just to fix our ideas, suppose that this t0 is just equal to 0, okay? So the integral here starts from 0. Okay, so I have to calculate the integral from 0 to t. Let's see. This coefficient here in front is common to everything, so I just put it here, v n I. The integral really involves just e to the I omega n I t. There are two terms, in fact. Let's write it like this. One has this minus omega t prime, and another one has plus omega. Okay? Clear? With respect to the single thing, you generate two because of the cosine having two waves, minus and plus. Okay. Now, the integrals are both very elementary. Let me just do it. It's v and I divided by I h bar. There is a factor 2, which I will put it here. And then the first integral is simply e to the I omega n I minus omega evaluated times t divided by whatever frequency you have here, right? This is the primitive. If you take the derivative, this is exactly that object. So you have to calculate between t and 0. So at t you get this, in 0 you get minus 1. Okay? The second term is entirely similar, so there is a plus, but now the denominator will be ni plus omega, and you will have e to the I omega ni plus omega t minus 1 again. Okay? Is this clear? Very, very simple. But hopefully you don't miss the points. Okay? Now, you see there are two terms, one with the plus and one with the minus. Now, for definiteness, let us assume that omega is positive. Okay? It doesn't make much of a difference if you consider it negative. I mean, the two terms would change role. Okay? So suppose that omega, by definition, is my positive frequency with which I perturb the system. All right? Good. At this point, you see that these denominators, okay, could be possibly small. For instance, suppose that omega ni is what? Okay, you have your spectrum of the unperturbed system. Okay, so these are the En. Divide them by h bar, by the way, so that we get rid of the h bar. Now, omega, if this is the initial state, omega ni can be positive. For instance, in a case like this, would be this difference between En and Ei. Okay? So you see, this is a case where you are trying to calculate the probability of exciting a system to a larger thing. So this would be greater than 0. Okay? Excitation. There is also the opposite situation, a de-excitation. So by opposite sign, you have omega ni less than 0 whenever the En is less than Ei. Okay? So this is de-excitation. They are both possible, okay? Unless, obviously, the initial state is a ground state, okay? Then, obviously, only the excitation is possible. But in general, if the initial state is some state in the middle, you can further excite or de-excite the system. Now, you see that it makes a very important difference. Suppose that you are looking at excitation processes, okay? Now you see when omega exactly or almost exactly matches one of the excitation frequencies which the system has in its spectrum, this denominator will become very, very, very small. Therefore, this coefficient, this term will become very, very large. As opposed to this, where now two positive quantities sum together and therefore really makes a small contribution. Okay? So, indeed, you could allow yourself under many occasions to drop simply one of the two terms. For instance, if you are doing excitation, then you just keep this. Okay? Because that's the important term that has a small denominator when you are exciting. So therefore, omega ni is positive. On the contrary, when omega ni is negative, you are exciting, the thing, de-exciting, the term that has a small denominator is this, okay? Because then to the negative thing, you sum a positive and you get almost 0. So this is important if you de-excite. Okay? So both are there, but to all practical purposes, especially when omega is closely matching a particular frequency difference, either one or the other will completely dominate the picture. Okay? So at this level, you could simply keep one and drop the other. The argument could be made very, very, you could say, okay, I say omega, okay, for instance, let's see. If omega is equal to omega ni, so it's omega ni means it's positive, so this is an excitation process, plus some small delta omega, then this term here will be what? This term here will be, the denominator is I, you subtract that, so you get minus delta omega, and the numerator is e to the minus I delta omega t minus 1, okay? If I'm not done any mistakes. The other term, on the contrary, would have a denominator that is quite large, I times 2 omega, so, or 2 omega and I plus delta omega, you see, because omega sums with the other contribution, and the numerator, whatever, is e to the minus the same thing, okay? So 2 omega n I plus delta omega t minus 1. So observe that there are two features. One is the denominator here, so if delta omega is small, you are close to a resonance. The denominator is small, and therefore the term is large, and it oscillates slowly. Because you see the same thing that appears in the denominator is also as an oscillation frequency. On the contrary, the other has a very large denominator, so a small prefactor, and it oscillates widely, okay? So both features are obviously pointing into the direction that you need to drop this if you are working in this close to an excitation, okay? So this is close to an excitation frequency. If you're working on the contrary close to a de-excitation frequency, then you must have, for instance, omega equal to minus omega ni plus some delta omega, and you can repeat the analysis, and you will see that this is now important rather than this, okay? That's it. This very simple integral gives you the coefficient. If you want the probability, you have to calculate the square modulus of this thing, okay? So in principle, again, there are two terms, and you would have the square modulus of the sum, but if you forget about one of the two, you will have the square modulus of a single thing, okay? So let us do this approximation, which is called resonant approximation. Okay? Which consists in dropping whatever term is not important with respect to the other, depending if you are in excitation or in de-excitation range. Okay? So if you are exciting, drop this. If you are de-exciting, drop this. Okay? At that point, you can calculate the probabilities, which are around now here. Let me eliminate this. So the probability, okay, of starting from I, ending up into an n, which is different from I, okay, at time t to first order. And I put here res, means in the resonance approximation, okay? Otherwise, I would have really the modulus square of both terms. So in the resonance approximation, I simply have the modulus square of this thing, which is the matrix element V and I divided by 4 h bar squared, okay? Times, for instance, the modulus square of this. Let's do the excitation case. Then the modulus square of this, okay, I write as, let's see, e to the I omega ni minus omega times t minus 1 modulus square divided by omega ni minus omega square. Okay? Good. Now, let us do a little massage to this equation. So is this clear? Where do I go? Do I get it?
Yes, minus.
Where?
I.
No, modulus square, not the square of I. if I take the modulo square of this, then I get the modulo square of the numerator, and in the denominator I just get the square of the different. I'm not getting I square, but modulus of I square. Modulus of I is 1.
No, I mean there's I.
Where?
In the sense V and I over 2IH bar.
Right. But the modulo square of this, again, the I is 1. Okay? Same argument. The I disappear except for there. Okay. So you see this is an oscillatory function. Okay? It oscillates as a function of time. Let us study a little bit more. So the denominator, as promised, contains the frequency difference. But let us rewrite it a little bit. So I can essentially put as a factor here e to the I omega ni minus omega t divided by 2, common to both terms. If I do that, then I will have the first term needs an extra t over 2. The next term, however, so the 1 now becomes minus e to the minus I omega ni minus omega t over 2. Okay? I've rewritten this object here as a prefactor which contains t over 2 times essentially two terms that now are a little bit more symmetric, you see? Because this has t over 2, this is t over 2, just the first has a plus, which with this plus gives me the full plus t, and this is a minus that with this plus cancels and gives me the 1, okay? So this thing should be modulo squared, and then I should divide by omega ni minus omega square, and then I should put the v and I modulo square divided by 4 h bar, okay? But now I realize that the modulo square of a product is the product of the two modulo square, so I can do this times the modulo square of this, and this is a pure e to the I, modulo square is 1, okay? So the advantage of this little trick is that now you see more clearly which function this is. It's a sine, okay? So let us write it in full. Well, really to have a sine, you would need what? You would need some factor 2i in the denominator, okay? So please verify that the factor 2, essentially you can use it from there, okay? So you see that there is a factor 2 then squared that you do have there, okay? So you can just drop the factor 4. Okay, this is one possibility. You can drop the factor 4, so v and I modulo square divided by h bar times the sine of omega ni minus omega t divided by 2, sine square, obviously, divided by omega ni minus omega squared. Okay? This is one possibility, but I prefer another. Simply, since you see you have omega ni minus omega here, and here there is a factor 2, let us put a factor 2 here. Okay? But obviously I have to compensate for an extra factor 4 out. Okay? So this is another possible way of writing exactly the same thing. Okay? Is it clear? Okay, now the nice thing is that now you can do better limits, for instance, when the frequency goes to that. You see, you shouldn't take only the denominator into concern, but also there is a numerator. And you know that sine of x divided by x behaves nicely. Sine x over x goes to 1, for instance. So you can take limits in a much better way. Okay? So let us see what this probability of excitation looks like. Let us plot it. Can I erase here? Well, I guess yes. Let me just. So, this probability, P1 resonant I to n different from I at time t, as a function of t, okay? How does it look like? Well, let's see. For t going to 0, first of all, what do you get? You get 0 because the limit, you see, you can, for instance, you can add a t here and the t obviously squared there. At this point, you can call this variable x, okay? And you see that you have sine square of x over x squared, okay? So in the limit where t goes to 0, this is exactly the well-known limit, sine x over x for x going to 0, so 1. So you see for the behavior for small t is just t squared. So this thing starts as a t squared, like that. Okay? And obviously you might say, okay, then what? Well, then it oscillates, right? Sooner or later, this will no longer be just 1. And if you keep increasing t, okay, what you will have is some oscillations, okay? Forget about now this thing has done its service, okay? So let me just drop it again. Now, as a function of t, you expect oscillations. By the way, oscillations still obviously positive things, okay? So things like this, right? Well, as a function of time, okay? So this probability, indeed, it touches, you see that even touches 0. Whenever the sign, the argument here is for instance, pi or a multiple of pi, you have 0 thing, okay? Obviously, you can try to figure out what happens when you go close to a resonance, okay? And you see that this thing will become rare and rare. Let's see. What is the, if I plot this thing rather than as a function of time, as a function of frequency for a fixed time, this is another useful way of understanding what is going on, okay? So let us also look at that. So now, different thing. For a fixed time, I look at this thing as a function of omega, okay? So t fixed, and now as a function of omega. What do I see? Well, better as a function of omega minus omega ni, obviously. Okay, so the 0 here will be an exact resonance. Okay, and you will have, in the limit in which this quantity goes to 0, you have what? You have essentially this quantity becoming 1, obviously, if you put the usual t squared there. So here you will get a value which is given by this quantity. Okay? So on resonance, you have a value modulus v n I squared divided by 4 h bar squared t squared. And then as you go out, this thing will now again oscillates as a function of frequency. But the nice thing is that obviously it goes also down. Okay? You see the difference between, well, not very nice. As a function of time, I mean, it has a purely oscillatory behavior. As a function of frequency, it is kind of sharply peaked there because this will decay as 1 over omega minus omega ni squared. In other words, as the square of the frequency difference, okay? And you can even tell me how big is this interval in frequency where you have the sharp central maximum. It's very simple. If you have to calculate where the sign touches 0, okay? And this happens when this object here becomes pi, okay? So this object occurs when omega ni minus omega times a certain time divided by 2 becomes plus or minus pi. Okay? So let us do the case where omega ni is greater than I mean, this case, omega greater than omega ni, so the positive case. Then you immediately see that this difference here, I write it better, omega minus omega ni times t is equal to pi over t. Okay? So this object here, omega minus omega ni, should be equal to 2 pi over t. Okay? So that's very important. You see that the width of the central peak in frequency, if you plot versus frequency, close to the resonance you are looking at, becomes sharper and sharper as you reduce t. Okay? So the more you let t go, the more the system is very sensitive to your frequency, while it somehow is less sensitive to other things. Okay? So in some sense, you need to have some large enough t in order to really be sensitive to a frequency. Why is that? This is very, I mean, physically intuitive. You are doing kind of Fourier analysis of your system, okay? So you are sending a certain periodic wave, see where, I mean, the frequencies at which the thing. Now, if you let the system get the periodic wave for a very short time, the system will not be really able to Fourier analyze it and say that and see that there is a definite frequency. And therefore, will respond a little bit also with other excitation. But as time passes, then the system recognizes that you are sending a nice periodic wave, and therefore it knows that there is a certain omega, and that omega is the commander, okay? And it responds nicely to that omega and very little to the others, okay? So, yeah.
If we let t to be large, then the probability of getting, w minus
That's
ni will be small, right? Because like t squared.
right. Okay, that is exactly the problem that I want to touch now. So in some sense, you want t large enough, okay, because you want to have a sensitivity to the resonance. On the other hand, as you noticed, if you really take t very large, naively this thing might just explode sooner or later and become larger than 1, for instance. Remember, this is a probability of excitation from I to n different from I. Now, this probability will never have to go larger than 1. Absolutely. Okay? So really, the time you need to have in order for believing yet perturbation theory has to be small enough that this is not going to be very large. Otherwise, you should account for second order, third order, and correct this result. I mean, the probability will not explode. It's fixed to be just bounded by 1. But the second order and third order and higher order correction will make this to occur. The first order alone would like to explode. Okay? So in some sense, t has to be large enough, but small enough. Okay? So there is a limit. Let me try to describe this to you better. Okay? So in some sense, you want for resonance to be clearly seen, t to be much larger than essentially 2 pi over omega ni. Okay? I mean, omega and omega, and this is the delta omega. Remember, this is the delta omega. Okay? So you want a small delta omega, so T, which is just 2 pi over delta omega. You want this to be small with respect to 2 pi over omega ni. Okay? This is much larger than that. Okay? So this on one hand. On the other hand, you want this quantity to be much less than 1. And therefore, you also want T to be much less than what? Just read from the thing, H bar divided by V and I. Okay? There will be a factor 4, but that's not important. Okay? Order of magnitude is H bar over that. Okay? So both these things have to be satisfied. This for resonance, and this for validity of first order. Okay? What does it mean? Well, put them together. It means that there must be a suitable window of T such that D can vary in a region which is much less than H bar over V and I, while still being much greater than what? 2 pi over omega n I. Okay? But this means, therefore, that this has to be much smaller than this. Otherwise, the window reduces to 0. Okay? So what you really want is that these two objects, okay, which are both times, you see, they are h bar over an energy, and this is 1 over a frequency. They have to be in this order. So this much less than that. Which means, very simple to establish, which means that h bar, omega, and I, okay, so the excitation energy has to be much larger. You see, I'm bringing this on this side and omega on this side. Much larger than, well, there are 2 pi's, evidently not particularly important, much larger than, strictly speaking, from this I would have a 2 pi V and I, okay? You can drop the 2 pi if you want, okay? So the excitation frequency has to be much larger than the matrix element that couples the two things, okay? So perturbation theory, in some sense, is governed by a matrix element divided by an energy difference. You remember the correction to the state? It looked like V n I divided by E n minus E I. Things like this always appear, okay? So this has to be small. The matrix element has to be much less than the energy you are looking across, okay? And this is exactly what this thing is telling us, okay? So don't believe to any perturbative results for so long time, or in any case, when you are coupling very strongly levels that are somehow closer in energy than the coupling you put. So in absolute terms, it is not that V and I has to be small. It has to be small with respect to the energy difference it couples. That's the important parameter. There's nothing small in absolute terms, okay? What do you mean an energy is small? An energy has to be small with respect to some other. And the exact thing is the coupling has to be smaller than the energy difference it couples. Okay? So is this clear to everybody? All right? So validity, to summarize, the validity of perturbation theory tells that V n I divided by, the unperturbed, I put again the 0 to remind you that these are unperturbed things. Okay? This thing have to be much less than 1. Okay. Questions? No. If there are no questions, we now use essentially what we have just now written to explain Fermi golden rule. Okay? Let me erase a few things. The right ones, however. If you're, well, I think I can erase the general setting here. Now, in the derivation of Fermi golden rules, you kind of, for instance, you can assume from the outset that you forget about the loser here, okay? So there is always a winner. Either the excitation wins over the excitations or vice versa, okay? So it is always one of the two factors. Remember, this was coming from the factor e to the minus I omega t in writing the cosine, and this was coming from the factor e to the I omega t, okay? We had both because we had the cosine. Now, let me do just a pure case. So forget about the loser, for instance, this, if I'm doing excitation. I just keep this. But also, I forget about the factor 2. In other words, my perturbation now will be V times e to the minus I omega t. Okay? You see the difference? Before I had the cosine, so something like this. Now I dropped this and that. Okay? Obviously, you might tell me, okay, this is complex, and therefore is in principle not Hermitian. Okay? Obviously, there is always implicitly in your mind that there is another process that makes everything perfectly Hermitian, but this process is associated to something that is a loser. Okay? So forget about the extra term and just concentrate on this. This tells me immediately, if I calculate exactly the same quantity, that the probability of exciting the system from I to n different from I, again, only for resonant, because I'm keeping only the resonant thing, that would be V and I, the same expression I had before. The only difference is, notice, that I am dropping also the factor 4. Okay? So I have this thing. Okay? And then I have the sine square omega n I minus omega t over 4, over 2, sorry, divided by omega n I minus omega over 2 squared. This is exactly the same expression you have there, except, forget about this, for the factor 4. Okay? Now, it's a matter of, just choice. I could really do the full thing from there. Not a big difference. Now, you remember that I was inserting t and inserting t there to show, for instance, important limits. Now, I want to do something slightly different. I want to take care of integrals rather than limit. Okay? In order to do that, let me do the following thing that you will understand only a posteriori. Let me just put a pi t and pi t here. Okay? Now you see, there is only one t, not t squared. So I cannot really reconstruct the same variables as there. There is one t less. You might be puzzled. Why do I put a single t and not just a t squared? So that, because of the following. The behavior of the function as a function of omega, or omega different, is just the same as that. I have just decided to rescale things with t. Okay? As a function of omega, it's the same picture you have there. So the same idea I had before applies. When t grows, this thing shrinks. Okay? Because you see the minima are just, well, you see it from there. Okay? So, in some sense, I am having something which becomes narrow, these are less important than this. And I would like to have also that the total integral is 1. Now, if the total integral is 1, then you understand immediately that this is something that is approaching a delta function, right? So I want now to create a delta function for you out of this sine square over thing. How do we make it? Simple. That's the trick. In other words, if I consider the following integral over dx, where x, well, forget, what is it? Yeah. I will call x this variable here. Frequency over 2, okay? So the integral over x, what you have there is sine square t times x divided by x squared, okay, times t, and then there is a 1 over pi. Okay? Now, you immediately see that now I can change variable and define tx, a new variable, but in order to compensate for this x there, I put a t and another t, and now everything is complete. In other words, now I call y tx, and this becomes integral in dy, by the way, from minus infinity to plus infinity, over pi of sine square of y divided by y squared. Okay? Now this integral is 1. You can check in the thing. Okay? So, in some sense, the reason why I put a single t is because there will be another t coming from the integral now. Okay? Before it was a limiting process, and therefore I needed both t to do the limit. But if I want to take care of the integral, 1 is enough. Is this clear? It's very simple, change of variables into integrals. Okay? In order to completely reabsorb t, you need to have only 1 here, because another one will come together with the measure. Okay. With that trick, you realize immediately that what I put here is a function, okay, which now increases linearly with t, not quadratically, okay? And is a function that becomes sharper and sharper, because as t increases, this becomes smaller, and whose integral over all frequencies is just 1. Okay? So in some sense, quotation marks, this becomes a delta function of this variable, which is obviously, the variable is really omega ni minus omega over 2. Okay? That's the important variable appearing there. You understand quotation marks because, it's in the limit in which t becomes large. But you might say, hey, wait a second. But if t becomes large, this probability explodes. Correct. In fact, what I define is not the probability, but I define the rate, which is the probability per unit time. Okay? So let me define the rate for exciting from I to n, which is the probability divided by time. Okay? So this is the probability per unit time. At this point, looks like a tremendous trick. I do have V and I modulo square over h bar square with a single factor pi. There is no longer a t. And this object here, quotation marks, is just a delta function of omega ni minus omega over 2. Okay? So the rate, probability per unit time, is a reasonable thing. Obviously, the usual assumption is that these things have not to become large. Okay? If a rate is so large that things immediately explode on your face, then forget, perturbation theory is not right. Okay? but the rate is a meaningful object to calculate if small enough, and in this limit will become just a very sharp delta type of thing, which essentially picks up only the resonant part, okay? With what coefficient? Pi modulo square of V and I squared divided by H bar square. Now, let us reconstruct better the delta. Now you see this is a delta of a frequency divided by 2. Not particularly nice. But you know that if I have a delta, let me just copy this. If I have a delta of alpha x, okay, this is essentially a delta of x. Do you know what factors you have to put? 1 over alpha, okay? The reason is, not alpha as one, the reason is, yeah, alpha is for me just a positive number, okay? The reason is that under an integral, okay, of f of x, you can change variable, okay, and call this y, and you will realize that in the change of variable you get essentially an alpha, and that expression holds, okay? So you can realize that the constant in the deltas have to be taken out, but put in the denominator. There is a similar thing if you have a delta of a certain function, okay, of x. Then you know that you have to look for the zeros of the function and put 1 over the derivative. Okay, so this is in some sense a simpler case because the function is linear and the derivative is simply alpha. Okay, so let us reconstruct with this the fact that you can put the 2 rather than here, and now becomes a nice 2 pi. The other thing is that this h bar, which is standing here, if you want, you can put it there, okay? But again, from the denominator, jumps into the numerator. So I can also do this, okay? Okay, one of it, okay? One remains, okay? So the rate, let me write it finally, is just equal to the matrix element square times 2 pi divided by h bar times the delta function of what? Of the difference in energies. You see this is En minus Ei minus h bar omega. Okay? So the omega with all the h bars has to match the frequency difference, and the rate then is multiplied by the modulo square of Vn plus 2 pi. Okay? This object here is called Fermi-Golden rule. It allows you to calculate rates for processes to occur in the lowest order in perturbation theory. It is really useful when the spectrum has very, very dense. Okay? So the En, after all, might be very, very dense. Suppose that you have an atom and you want to calculate what is the excitation probability for ionizing the atom, so taking the electrons off. It means that the final state is a continuum, okay, an electron in a plane wave type. Then there are many, many En, very, very dense, okay? So you are really not looking for a particular sharp resonance. You are going into a continuum. And therefore, it makes sense, really, to work with delta function for a reason that I will explain to you now. If you really have a discrete spectrum, so you want to excite from the 1s, for instance, to the 2p, then there is not much sense to talking about a delta. There is always a certain width associated to this, okay? In some sense, a more reasonable thing is to keep this. This keeps the width. You can excite with a frequency which is not infinitely sharply equal to the difference. You can allow for a certain width. This width is inherently related to the finite time that you allow in the process, and therefore the system is tolerant in some sense. By the process, it was not able to perfectly analyze your Fourier spectrum, and it was accepting even some small deviation. Okay? So if you excite from a discrete to a discrete, account for the width by, for instance, keeping the sign. However, if you are going to a continuum, there is no need to keep really this width, and you can describe everything with a nice delta function. In fact, often, oh my God, it's quite late. I want to do an exercise now, which I'm not obviously be able to finish. What you do often is the following. Maybe. Just a second, I'll look for, there's a missing page here. Ah, there it is. Okay. Okay, so this is a given rate, but you often consider a situation where you excite your system from a certain initial state, which is a discrete level, to a continuum. Okay? So the energies here are a continuum, En, while Ei is a discrete thing. Okay? So you can actually, the continuum means that for every given interval, whatever small, you have a very large number of energy levels. Okay? And indeed, you know that you can introduce what is called the density of states. Okay? A density of states is essentially a function that tells you that in a given interval, okay, of energies, you have per unit volume so many number of states. Okay? At that point, if the matrix element depends very slowly on energy, for instance, all those energies which are slightly different inside this interval delta A, E, have a slightly different matrix element. But suppose that delta E is very small, then roughly they will have the same matrix element, V, say, I to, I mean, V and I essentially will depend only on the energy, roughly speaking, okay? So what you can do is that you can sum the rate here. So what you do is the following. You take the rate from I to N, different from I, and you sum over all the N's, okay, which fall into the interval VE around a certain energy E, okay? At this point, the sum of delta functions really reconstruct for you the density of states, okay? So what you have is that this sum of elements will be like something like this. Will be the integral between, say, the final energy En minus dA over 2 and En plus dE over 2, okay? So I'm describing this as a final energy plus or minus a certain small thing, times the delta, the deltas here, and the deltas have En minus Ei minus h bar over omega, and, well, and there is some 2 pi and h bar. And what I'm telling you is now essentially the following. This coefficient here depends very, very little on N, on the energy, on the number. So you can drop it out, okay? And the integrals of the delta just give the density of states, okay? So the result is simply 2 pi over h bar, the final energy, the final matrix element, I call it just F, means the final, times the density of states at the energy Ei plus h bar omega, okay? So it really depends on how many states you have at that energy En. Okay? So you have to account for this. Okay, this could change things, for instance, because, for instance, close to this 0 here, the density of states might include less states or more states than far away. And this will change the rate in a way that somehow doesn't depend on the matrix element, but it depends on the number of states that you have access to, which could be large, small. You know, the density of states, for instance, in 1 dimension, or in 2 dimension, or in 3 dimension is very different, right? So in 3 dimension is something like this. I'm talking about a free electron model, okay? So the density of states will do something like this, square root of omega. In 2 dimension will be flat. In 1 dimension will do something like this. Probably you have seen this with Sandro's candle. Huh? Okay, yes. I mean, these are density of states effect, okay, which would change the way the rate looks in some sense, but not because of the matrix element, but because of the number of states that you can access at that energy, okay? Okay. That's it, okay? This is just to tell you that most of the use of the Fermi-Golden rules are really done when this delta is then integrated over into energy to produce a density of states, okay? This is the only message I wanted to give. Now, exercise, let's see if we can do it. Suppose that I have the promised electromagnetic wave impinging on an atom, okay? So the question is to calculate. You have an atom, for instance, a nitrogen atom, just our old beloved hydrogen atom, and you send to it an electromagnetic wave which will perturb, okay, will be our V of t. How does it look, the Hamiltonian? Now, suppose that the electromagnetic wave is described as a classical field, okay? You might object to that, because after all, you know that the fields, electromagnetic fields, are quantum objects in the sense. Photons are the ingredients of those fields, and therefore you should use creation operator for photons, and so on and so forth. This would, however, lead us to essentially quantum electrodynamics, so a theory of quantum electrons and quantum photons interacting together, which is not what I want to touch on. So I will consider the electromagnetic field as a classical Maxwell type of field, okay? So how does it enter? For instance, it enters into several places. You know that if the field has a vector potential, it enters like that, okay? And this vector potential, if the field is time dependent, will depend on t, by the way. And in principle, electromagnetic fields will also generate, so you will have the square over r, and you will also have a magnetic field there, so some 2 mu b times b times the spin, okay? The Zeeman term, okay? Now, you realize that this, so for instance, you remember that you can also expand this. Suppose that the field was a uniform, blah, blah, blah. You can always expand the square and get things like H0, the hydrogen atom Hamiltonian, plus E over mc A dot P, plus 2 mu B. This would be just G0, okay? I'm putting it to 2. 2 mu B B dot S plus the square of this, E square over 2mc square A square. Now, first thing, I want to really get rid of a few terms. This term is in principle there, but you can easily estimate that is much less than this, okay? You can calculate. Okay, let's be definite, and I assume what? I assume that the vector potential that is impinging I can always describe the wave just with the vector potential, right? This allows to describe electric and magnetic fields, because you know that the derivatives over time will give you the electric field, the rotor, the curl, will give you the magnetic field. So let me just assume this. K dot R minus omega t plus the complex conjugate. Okay? So let us look at this particular A. A0 is a constant vector. Okay? Now, let us do a few particular cases. Let me assume that K and A0 are orthogonal. Okay? So A0 is orthogonal to the direction K. This immediately, if you check, immediately tells you that the divergence of A is 0. This is very nice, because if the divergence of A is 0, I know that I do not have to worry about the order in which the A and the P are set into that thing. Okay? So this is a particular choice of gauge that is particularly useful. Now, the other particular choice. Let us say that, for instance, A0 is just along Z. Okay? So I just write it as some constant times Z. While K, I take it along Y. Okay? So for me, K will be just that. Okay? So this is certainly compatible with the previous one and makes life slightly simpler. You can realize immediately that you have here A0 Z times the cosine of K Y minus omega t. Okay? So this vector potential is a vector potential along Z, which moves like a plane wave, okay, with a certain K and omega in direction Y. Okay? Good. So what is the electric field? Well, the electric field, you know, is minus 1 over C, the derivative of A. Okay? Calculate immediately, you have minus some quantity which is related to A0 and C, still along Z, and this time you have to take a derivative. Oh, there is also an omega, obviously, occurring there. But taking the derivative of the sine gives you the sine of K Y minus omega t. Then you can calculate B. B is this time the curl of A. Just calculate the curl, and you will notice that this is equal to K A0 times X this time, and still the sine of K Y minus omega t. Okay? So electric and magnetic field are orthogonal, as you expect, and they have a sine Ky minus omega t. Okay, now this is the wave. All right, now let us look at this term and that term. If you calculate the ratio, usual order of magnitude, 2 mu b, b dot s, divided by E over mc, A dot P, order of magnitude, it's simple to get the results. You see that P, okay, A would be, so let's see, the denominator, E over mc, then this would be A0, and P is of the order of h bar over the bone radius, okay? The momenta has to be h bar over thing. Now, on the contrary, here, this thing in units in which h bar is 1 is essentially 1 or 1/2. So what you have there is E h bar over mc, the Bohr magneton, times B. But B is what? B is K A0, okay? K A0. So immediately see that A0 and A0 cancels. the MC and MC cancels, the E and the E cancels. In fact, the H bar and the H bar cancels. Everything reduces to a miserable K AB. Okay? So the ratio of these two things is the wave vector times the Bohr radius. So what I'm really assuming is that I have a wave, an electromagnetic wave, in a range of frequencies where the wave vector is much longer than the, I should write, probably it's better if I write this as in terms of wavelength. So this is 2 pi AB over the wavelength, okay? So I want a wavelength that is much larger than the Bohr radius, which means, for instance, visible light would be fine. In order to have wavelengths in the Bohr radius thing, you must have X-rays, okay? So I'm not doing absorption of X-rays. I'm doing absorption of some visible or ultraviolet, but not that large, okay, in energy, and therefore this is much less than 1, okay? So for all frequencies that are not high in the spectrum, you don't need to worry about this term. By the same token, obviously, well, you don't really need to invoke A square if you have A, because this is quadratic and this is linear. So these are small things, and therefore the A square will be much smaller than that. Okay? You can verify it. So all you need is really this. And obviously this object here is a function of t now. In fact, let us just immediately write what it is. So I now drop everything else, okay? And I say the Hamiltonian is H0 plus E over MC A0. It's along Z, okay? So what it counts is just PZ, the operator PZ. And then I have cosine of Ky minus omega t, okay? So you see it's a function that depends on time in the promised pure monochromatic way, but you see that Pz and Y appear. So I have to calculate matrix element where I keep into account that these are the electronic momenta and position, all right? Calculate the matrix element according to that. Is this clear? Okay. Well, in fact, you can very easily realize that this, okay, let me write this as the usual factor 1/2, two terms. One is e to the I k y e to the minus I omega t, and the other is the opposite, e to the minus ky e to the I omega t divided by 2. That's the way you write a cosine always. Now, you remember in our previous discussion that the absorption part, okay, was all related to this. Essentially, this lets the energy increase. Remember in the excitation, who was winning, who was losing. This was the winning guy when you were exciting. This was the winning when you were de-exciting, okay? So you can actually drop this if you are describing the excitation process, or drop the other if you are describing the de-excitation, okay? So let us concentrate on excitation, and we keep just that, okay? So I'm looking for En greater than Ei, okay? Excitation. What time is it? Oh, we still have 5 minutes. Probably we'll make it. Okay. Is everything clear? Reasonably clear, okay? You're supposed to go over the notes and see that you understand the algebra and everything, okay? Good. So now we immediately have the result, for instance, okay? We can calculate either in this delta function approximation or in the sine square object the rate, okay? So for instance, I write here with the sign, okay? So I ignore the delta story. So the rate for exciting the system from some initial state to some final state n will be the modulo square of the matrix element, which I will now tell you what it is, divided by 4 h bar square, the usual sine square, omega ni minus omega t over 2, divided by omega ni minus omega over 2 square, and since I'm looking at the rate, I put the factor 1 over t there, okay? The matrix element is simply extracted from here. You see, this is V, okay? Forget about the thing. It's just this piece that you have to sandwich between the initial and final state. So it's equal to E A0 divided by MC, and then I have to take the matrix element between En and, sorry, phi n and phi I of what? Well, Pz e to the I k y. Okay? So this is the matrix element. Now, well, unfortunately, I just erased it. But if you remember, we evaluate a certain ratio of two things, and we discovered that k times AB, or if you want 2 pi AB over lambda, in the regime in which I am working, is much less than 1. Okay? So k is small with respect to the atomic inverse length, to the atomic momenta, which means that the photon has a very, very low momentum with respect to the, okay? So we'll not be able to really change much in the momentum of the particle. And in some sense, this implies that, you see here, y is an electronic position. These two-wave functions are localized around a certain Bohr radius, and therefore k times the Bohr radius, which is what appears there, is a small quantity. So you might as well drop this and put to 1. Okay? This is an approximation, which is, however, quite good for visible light, for instance. It's called dipole approximation. Okay? It means neglecting, by the way, these two things commute. Okay? You could put Pz and e to the ikx. Neglecting e to the ik positions with respect to momenta. This is the so-called dipole approximation. At this point, you realize that the matrix element that appears is exactly the same matrix element. Well, there's still one extra piece of theory that I have to do for you. We have not seen, until now, matrix element of momentum. We have seen a case with a matrix element of position. Remember, if I put an electric field, Stark effect, electric field X. So that case we have done. And we know what states I can couple. The P we haven't. But the P and the X are relatives for a very simple reason. If you calculate the commutator of Z with H0, then obviously Z and E square over R commute. So the whole thing is identical to the commutator of Z and P square over 2M. But Z also commutes with the other components of the momentum. So all you need is this. And this commutator is very, very simple. It's just I H bar over M Pz. Okay? So Pz, apart from some factors, is really the commutator of Z and H0. Okay? And now look at the trick. I have here a matrix element of Pz. So phi n Pz phi I, okay? And I use this trick, and I re-express Pz in terms of this commutator. So this would be M over I h bar, the matrix element of the commutator of Z with H0 between the two states. But this is nothing but the matrix element of ZH0 minus H0Z between the two states. Okay? Same factor. You follow? And now you see that this is simple because H0 acting on the initial state will give me the initial energy, and H0 here acting on the final state will give me the final energy with exactly a minus sign. So this thing is nothing but what? It's ENI, En minus EI times the matrix element of the Z operator, okay? Times M divided by IH bar, okay? So in essence, you can forget the complication here that is P. It's like having Z, and Z we have analyzed already, okay? So like in the linear Stark effect, for instance, you can put everything in here. I mean, it's in the notes. No need to insist on this. You can do close the formulas and have expressions now for the matrix element you need. The important thing is that the presence of this factor here. Now I can ask you, for instance, a very simple question, which now becomes simple. Which are the final states that you will excite if you start, for instance, from the ground state? So you have a system in the ground state, 1s. You send an electromagnetic wave of this type, lowest order in perturbation theory, to which states n you will couple? Which will you excite? You immediately realize that you must have a matrix element of Pz, or if you want, of Z, different from 0. And you realize that, for instance, by parity, okay, the two states have to have different parity. Okay, so the 1s will not couple, for instance, to the 2s or the 2d, or the 3d, sorry. Okay? The 1s might couple to the 2p, to the 4f, for instance. That's okay. But now we know that there is another selection rule, angular momentum. We already did this for Stark effect. And we discovered that Z is a vector and can change the angular momentum by at most 1. Okay? So from L equals 0, you can go at most to P, not F. Okay? So, end of this discussion, by sending the wave, you will excite 2P, 3P, 4P, and so on. Okay? Obviously with different degree of thing, because the matrix element do depend on which level you are considering. But the fact that they are different from 0 or equal to 0 is a selection rule that you can just say without calculating anything. Okay? So this is already something useful. So you can calculate rates in this way. And obviously you can calculate ionization rates, okay? The probability of exciting the particle in the continuum. There you have to do this Fermi-Golden rule type thing. You have to account for the density of states and things like this. Okay? In principle, this is all contained in what we have done. I think that this is enough to give you an idea. Okay? So please try to go over the notes carefully. Questions? So the next chapter of the story will be more than one electron, okay? So we have done the most important things of one electron theory. So from next time, which is Friday, we will start discussing many particles, so what it means to be a fermion, a boson, things like this, okay?